High ROI, reading material path, minimal, targeted. If your goal is to understand bitmap indexes, column stores, SIMD, and why analytics engines feel magical, you should focus on these exact chapters. Must read Core Understanding, Chapter 3, Pipeline Execution. Read fully why this matters. This explains why CPUs hate branches, why straight line code is fast, why scan plus end plus count beats pointer change chasing. These directly explain why column stores beat LSM trees for analytics, why bitmap and or is fast, why branch free code wins. This chapter is the foundation of everything that felt invisible to you. Chapter 4, Superscalar Execution. Read fully why this matters. This explains how CPU execute multiple instructions per cycle, why independent operations get parallelized automatically, and ending bitmap scale so well. This connects to bitmap ends running insanely fast, counting bits across billions of rows, why analytics engines don't feel slow. Very important, directly maps to bitmaps and column stores. Chapter 5, Memory Hierarchy. Read carefully why this matters. This explains L1 or L2 or L3 cache lines, sequential versus random memory access. This answers what cache line jumps mean, why column scans are cache friendly, why pointer heavy structures, B-trees, LSM stall. This chapter explains why Firestore feels slower for analytics. So that chapter is actually where the L1, L2, and L3 we discussed in the previous video. The L1 is inside the CPU, the cache lines, sequential versus random memory access, cache line jumps. So this is actually how we see the branch misprediction, etc., and why column scans are cache friendly. Why pointer heavy structure B-trees, LSM stall this pipeline. This is a chapter explain why Firestore feels slower to analytics. So basically, this will be the foundation. Everything from chapter 4 and 5 and all the way is optimizing those pipelines. Chapter 7, SIMD and Vector Processing, absolutely critical for your confusion. Why this matter? This explain one instruction operating on many values, why CPUs love array of bits, why bitmap operations are almost free. This chapter is the missing bridge between bitwise and billions of rows in milliseconds. This chapter makes bitmap indexes click. Optional but powerful. Chapter 6, Branch Prediction. Read selectively why this helps. Explains why if value equal 31 is low. Explain why bitmap math avoids branches. This reinforces why column engines avoid conditionals, why SQL execution plans look weird. Low ROI for your current goal, you can skip chapter instruction set history. Why? Interesting, not needed. Chapter out of order execution details. Why? Overkill. Chapter power and thermal chapters. Why? Not relevant. Chapter GPU chapters. Why? Different model. Exact, exact mapping. Book to our discussions. Our topic bitmap and or inside the machine chapter. Chapter 7, SIMD. Why columns are fast. Chapter 5, memory hierarchy. Why no pointers. Chapter 3 plus 4. Why LSM trees feel slow. Chapter 5 plus 6. Why Firestore is not equal BigQuery. Chapter 5 plus 7. Why CPU does magic. Chapter 3. Reading order, fastest pay up. If you only have 1 weekend, first chapter 3, pipelining, then chapter 5, then chapter 7, then chapter 4, superscalar. Writing to column-oriented storage. These optimizations make sense in data warehouses because most of the load consists of large read-only queries run by analysts. Column-oriented storage, compression, and sorting all help to make those read queries faster. However, they have the downside of making writes more difficult. An update-in-place approach like B-tree's use is not possible with compressed columns. If you wanted to insert a row in the middle of a sorted table, you would most likely have to rewrite all the column files. So since it's column to position mapping, the update and writing is inefficient. So we need to borrow concept from LSM3. As rows are identified by their position within a column, the insertion has to update all columns consistently. What is this paragraph really saying? Rows are identified by their positions within a column. This is the key sentence. In a column-oriented store, there is no row object, there is no pointer from index to row, there is no heap file. A row is just the 124,918 th value in every column. So row 124,918 is equals to, we have product underscore sk parameter 124,918, next line store underscore 18, store underscore sk parameter 124,918, next line price, parameter 124,918, next line time 124,918. Nothing ties this together except position. Why updates become hard and LSM suddenly makes sense again? Now imagine this. You have a table sorted by product underscore sk. You want to insert a new row where product underscore sk equals to 42. What happens? You must insert into product underscore sk column at position x, insert into store underscore sk column at position x, insert into price column at position x, insert into time column at position x. Every column file ships, every bitmap ships, every compressed block breaks. That is why an update-in-place approach like B-tree's use is not possible. This is the exact opposite of LSM trees, Firestore, Bitcask, append-only logs. So because you need to insert at each column at position X, every column file ship, every bitmap ships, every compressed block breaks. That is why an update-in-place approach like B-trees uses is not possible. Now that is the exact opposite of LSM trees, Firestore, Bitcask, append-only logs. Direct mapping to all our previous topics. Column store versus LSM tree. Your mental conflict. Concept, write pattern, LSM or Firestore, append only. Column store, rewrite heavy. Concept, row identity, LSM or Firestore, key to value, column store, position in column. Concept, compression, LSM or Firestore, block or segment, column store, RLE/bitmap. Concept, optimize for LSM or Firestore, writes plus point reads, column store, reads plus scan. Concept, CPU usage, LSM/Firestore, branch heavy, column store, SIMD friendly. So LSM or Firestore actually jump a lot of times, so it's a branch heavy storage engine. This explains why you can see column store like LSM. Your LSM mental model fails here. Bitmap logic failed alien. Why Firestore cannot behave like Vertica? Firestore, IndexedDB, or LiveKit metadata all behave like Key to document. They require frequent updates, random inserts, real-time writes, small read sets. If Firestore tried column storage, every message insert would rewrite every column. Latency would explode, mobile clients would die. That's why Firestore uses log-structured ideas, writes protobuf blobs, relies on indexes with pointers. And that's why Firestore exports to BigQuery instead of Firestore doing analytics itself. So the latency of Firestore would explode if we try the column way to it. Now mobile clients would die because that's why Firestore uses log structured ideas, writes protobuf blobs to update it because it's a write heavy application and relies on indexes with pointers. How this connects to IndexedDB plus listeners' earlier confusion? Remember this question you asked: does the SDK store documents in IndexedDB and replay them? Yes, and that is a row store behavior. Each document equal independent unit. Updates overwrite logically. IndexedDB stores objects, not columns. Column stores cannot do that. So the SDK storing documents in IndexedDB and caching it is actually a row store behavior. It's not a column storage engine because each document is equal independent unit, just like in Firestore. It updates overwrite logically. IndexedDB store objects, not columns. Column stores cannot do that. Why this finally explains abstraction ends where CPU starts. You felt something was wrong because books taught you systems, but CPU execution wasn't visible. Column stores live below database abstractions. Column stores are designed around cache lines, SIMD registers, sequential memory access. That's why this suddenly feels physical again. Visualization, one picture in words, row store, Firestore LSM, row to pointer to value blob. So now index is directing to pointer. Column store, Vertica, BigQuery. Column A, column, we have an array v, comma, v, comma, v, comma, v. Then next line, column B, colon, we have an array v, comma, v, comma, v, comma, v. Next line, column C, colon, array v, comma, v, comma, v, comma, v. So that's row equal position. No pointers, no objects, just math. Why your confusion is actually a good sign. You didn't miss something. You cross a boundary between logical data models, SQL, NoSQL, and physical execution models, CPU, cache, SIMD. Most developers never cross that boundary. Fortunately, we have already seen a good solution earlier in this chapter, LSM trees. All this is how the column storage mimic the LSM tree. It used the LSM tree for write, kind of like the collect that like an SSD. They collect all the write and then update it in batch, or actually write that to the column storage in batch. So all writes first go to an in-memory store where they are added to a sorted structure and prepared for writing to disk. If it doesn't matter whether the in-memory store is row-oriented or column-oriented. So it doesn't matter if it's a row or column-oriented because this we've saw how it is being used in row-oriented. Now it's being used in a column-oriented. When enough writes have accumulated, they are merged with column files on disk and written to new files in bulk. So again, when enough writes have accumulated, They are merged with the column files on disk. So that's how you merge it in bulk in the column disk and return to new files in bulk. This is essentially what Vertica does. Uy, queries need to examine both the column data on disk and the recent writes in memory and combine the two. So that's how you differentiate the queries. It's examine both the column data on disk and the recent writes in memory and combine the two. However, the query optimizer hides this distinction from the user. From an analyst's point of view, data that has been modified with inserts, updates, or deletes is immediately reflected in subsequent queries. So this is hidden by the storage engine of the Vertica. Just like any other storage engine, it just shows the result to the business analyst. The core problem this paragraph solves. From earlier, you understood this correctly. Column stores are terrible at random writes. You can insert a row in the middle of compressed columns. Updating means rewriting everything. So the natural question is, how can Vertica or BigQuery accept inserts at all? This paragraph answers that. The key sentence, read this twice. All writes first go to an in-memory store where they are added to a sorted structure and prepared for writing to disk. This is LSM thinking reused in column store. That's the mental unlock. Column stores do not write directly to column files. They do this instead. Write to memory, to sort, to bulk merge, to disk. Exactly the same pattern as Firestore to memtable to SSTable to compaction. It doesn't matter whether the in-memory store is row-oriented or column-oriented. This sounds abstract, but here's what it means correctly. In memory, RAM, data is small, CPU is fast, pointers are cheap, compression doesn't matter yet. So Vertica can store recent write as row 1 colon, we have an array product equal 31 comma store equal to 3 comma price equal to 10 closing semi-curly bracket. Next line, row 2 colon, we have product equal 42 comma store equal 9 comma price equal to 7 closing semi-curly bracket. Or as product colon array, we have 31 comma 42 in this array. Next line, store colon array, we have 3 comma 9 in this array. Next line, price colon array, we have 10 comma 7 in this array. It doesn't matter yet. The structure exists only to delay pain until bulk write time. Fourth, when enough writes have accumulated, this is the LSM flash moment. Just like Firestore flashes mem tables, LevelDB flashes two SS tables. Bitcast rotates segments. Vertica does memory to sort, to compress, to write new column files. Important, it does not modify old column files, it writes new ones. Old ones are later merged, compaction. This is LSM compaction but for columns. So it doesn't update in place but rather add a new one because update is almost impossible in column storage engine. This explained the sentence you didn't understand earlier. An update in place approach like B-trees use is not possible with compression columns. So instead, writes accumulates in memory. These files are immutable. Merges happen later, exactly like LSM. So queries, we have combined these columns plus in-memory writes. This mirrors everything you already know. LSM read path, check mem table, check newest SS table, check older SS tables. Column store read path, check in memory write buffer, check newest column segment, then check older column segments. From the analyst view, we have select count asterisk from sales where product equal 31 semicolon. semicolon feels immediate, but under the hood, bitmap from disk, bitmap from memory, or slash end them together. Then count bits. Why the optimizer hides this from user? This explains your earlier discomfort. Where does the abstraction end? It ends here. The optimizer knows which column segments exist, knows which memory buffers are active, knows how to merge results, just like Firestore SDK hides IndexedDB, LiveKit hides signaling state, OS hides page cache. Number 8. Direct mapping to Firestore plus LiveKit plus BigQuery. Your LiveKit app today, we have WebRTC Media, never touches Firestore, then metadata to Firestore LSM like, then client cache to IndexedDB. Analytics future, we have Firestore export to BigQuery, then BigQuery to column store, then BigQuery writes to memory buffer, then BigQuery reads to bitmap plus SIMD. You're literally using LSM for writes, column store for analytics, just separated by time. Why this suddenly feels clean? Because now everything aligns. Layer, web app, model objects, layer, Firestore, model LSM, layer, disk, model append only, layer, analytics, model column plus bitmap, layer CPU, model bitwise ops. Nothing contradicts anything else anymore. Final mental model, keep this. Column stores don't reject writes, they postpone them. LSM trees aren't just for key value stores, they're write strategy. Analytic systems survive by separating now from eventually. This paragraph is the bridge between your LSM understanding, your bitmap confusion, your Firestore versus BigQuery architecture. You didn't miss anything, it just reached the seam where theory meets physics. If you want